welcome to The Explainer. Have you ever stopped to think about how we went from believing the world was run by, angry gods and random chance, to actually understanding the fabric of reality itself? Well, it wasn't just one big aha moment. It was the invention of a powerful method, a playbook, really. And today, we're going to open it up and see how it works. For most of human history, the world just seemed chaotic. A storm, a good harvest, getting sick. It all felt like the universe was just making it up as it went along. But then a new idea popped up. What if it wasn't random? What if there were rules? And this is really where the game changed. A handful of thinkers, these early natural philosophers, they made a pretty radical bet. They said, hey, what if the universe isn't chaos? What if it's a giant predictable machine? And the craziest part of their bet, that we could actually figure out how that machine works. So, where did they even start? Well, they started by doing what we all do, just looking around and thinking about it, right? They watched an apple fall from a tree, they tracked the movement of the stars, and they kept asking that simple question, why? Their whole approach was to try and use pure logic to figure out the universe's rulebook. Okay, but that led to a massive problem. You can watch apples fall all day long, but how do you actually prove the rule that's making them fall? Especially when you've got things like wind and air resistance messing everything up. For almost 2,000 years, this was the wall that nobody could get past. And then the breakthrough happened. This is the exact moment when philosophy starts to become what we now call physics. And it's pretty much thanks to one guy who realized that to understand nature, you can't just sit back and watch it. You've got to poke it. And that person was Galileo. So what made him such a game changer? It was this. He stopped just observing the world as it is. Instead, he started creating these simplified artificial versions of the world right there in his lab, a place where he was in charge, where he could control the variables and ask super specific questions. Think about it. An object just falling through the air is way too fast to measure accurately, especially with the tools they had back in the 1600s. But a ball rolling slowly down a ramp? Hey, that's just falling in slow motion. By setting up this controlled little process, Galileo could isolate the force of gravity and finally get a good long look at it. And that right there, that was the revolution. The experiment acts like a filter. It gives you the power to strip away all the messy, complicated stuff from the real world, air resistance, wind, friction, all of it, until all you have left is the pure, clean signal of the one law you're trying to figure out. Okay, but that brings up a really big question, doesn't it? How on earth can a little ball rolling down a perfect ramp in a lab tell us anything about, say, a bird flying through a hurricane? How do you connect that clean, simple experiment to the messy, complicated real world? Well, the answer is physics' secret weapon. To build that bridge from the perfect world of the experiment to the messiness of reality, physicists use this absolutely essential tool. It's an idea, really. It's called the model, and this is where so much of the genius happens. So, a model is not reality. Let's be clear about that. It's more like a caricature. Like in a political cartoon, where the artist exaggerates a couple of key features to make a point and just ignores everything else. A physics model does exactly the same thing. It throws out all the noise so you can focus on the one or two things that actually matter for the problem you're trying to solve. And look at how this plays out here. On the left, you've got a real object with all its complexity, its shape, its material, the air pushing against it. On the right, you have the physicist's model of it, just a mass point. That's it. All the other details, shape, air resistance, they're just tossed out. For this problem, the only thing the model cares about is its mass. And here is where it all clicks together beautifully. When you take real objects and put them into the controlled world of an experiment, like a feather in a cannonball in a vacuum chamber, suddenly they behave exactly like the simple model says they should. In its beautiful simplicity, the model captured the fundamental truth of the situation. So now we have our two key players on the field, the experiments, which gives us the hard data, and the model, which helps us make sense of it all. But the real engine of discovery, the thing that drives science forward, starts when these two begin to talk to each other. It's this constant back and forth. You start with a model, and that gives you a theory. The theory makes a specific prediction. Like, if I do X, then Y will happen. So you go into the lab and you design an experiment to test exactly that. If it works, awesome. Your theory just got a little stronger. If it doesn't work, that's even better, because you just learned something new. So you go back, you fix your model, and you start the cycle all over again. And this dialogue, it's a two-way street. Sometimes you have a powerful theory, like quantum chromodynamics, that basically tells scientists, hey, if you build a machine and look right here with this much energy, you should find a brand new particle. And sure enough, they do. But other times, it's the experiment that just completely shatters our existing theories. The Michelson-Morley experiment found something so bizarre about the speed of light that it literally broke physics at the time, and that paved the way for a guy named Einstein to completely rebuild it. It's a real partnership. All right, let's bring this home. After all this, how does this entire process, this playbook, build our whole understanding of the universe? What's the ultimate payoff? Well, the ultimate goal of this entire process, this whole dialogue between experiments and theories, is to build a complete, fundamental picture of reality, to trace all the complex things we see around us back to a few simple, elegant laws about the basic building blocks of the world. And using this playbook, we've gone on this incredible journey, peeling back the layers of reality like an onion. We started with the big stuff we can see, and we figured out that it's made of molecules. Then we looked inside the molecules and found atoms. We cracked open the atoms and found a nucleus and electrons, and we just kept going, deeper and deeper, until we got all the way down to the most fundamental things we know of, quarks and gluons. And here is the truly amazing part. The same basic playbook works at every single level. It doesn't matter if you're trying to understand how an entire galaxy spins or what's happening inside a single proton. The process is always the same. You build a model, you make a prediction, you test it with an experiment, and you repeat. So when you really think about it, the most important thing physics has given us isn't just a big pile of facts about the universe. It's a method. It's a reliable, repeatable, self-correcting process for figuring things out. It's a playbook for how to have a conversation with the universe and actually get answers back. And that is what's so incredibly exciting. The playbook is still wide open. We have these enormous mysteries left to solve. What is dark matter? What's up with dark energy? The game is far, far from over, and the next revolutionary discovery is just out there, waiting for someone to run the next play.